Hello and welcome to today's video. We will talk about the Infrared Telescope Facility ITF or IRTF. Last week I have published a video about UK IRT, which is an observatory on the same mountain on Mauna Kea. And we will also wonder about the different fates of these two observatories, which are actually quite similar and opened in the same year. First, the outline is the same as always in these series of presentations. History and purpose. I didn't find much on the history actually. Equipment of the observatory, which tends to be quite complicated, but I won't go into detail too much. Then geography, some results or the general direction that the work in this observatory has, and in the end a short summary and outlook. This observatory is owned by the US National Facility for Infrared Astronomy and was built to support the Voyager missions. So whenever the space probes Voyager 1 and 2 visited planets, it was important to have both preparatory observations and also follow-up observations, which had to be done from the Earth. So this is what this observatory was for originally. And it is open to the entire astronomical community, but 50% of more have to be projects about solar system studies. And there are 8 members that decide on the time allocation, and of these 4 members, of these 8 members, 4 have to be solar system specialists. Then the investigators have an 18 months proprietary phase, which means after 18 months their data go public, which I think is quite common in astronomy. Normally I think it's 2 years, but here it's 18 months. So in this time they have to prepare their publications, and as soon as the publications are out, the results are out anyway, and they have their merits, and then the data can go public, which is a very good thing. The equipment is, the telescope has a diameter of 3.2 meters, of which 3 meters can be used, and it is a conventional Cassegrain design with an f of 38. But in the prime focus, if you use the primary mirror only, it has an f of 2.5, which is good for survey work. They said somewhere that is the 3rd largest dedicated infrared telescope in the world, although we know that the point dedicated infrared telescope is important here because you can measure on larger telescopes with an infrared detector. And NASA pays $6 million per year for this telescope. And then there are lots of instruments. I won't discuss them in detail here, all of them, because it repeats itself a little bit from other observatories we studied. Something I have to mention is this shell spectrograph, which is quite a good one, with a very good resolution of the spectrum. And the MIRC, this acronym reminds us of the MIRI in the James Webb Space Telescope. That's not accidental, because it's also a relatively long wave camera with also spectrographic capability. And interestingly, they have their own instruments, but they also have guest instruments that are there, which means probably universities that built them, they just leave it there and people can use them. Not only the people who built them, but also the community. But they are free to take them away and move them to another observatory if they want to. And that's an important point. The mirrors of the telescope is one thing, but the detectors are very, very important. And as we'll see, also what comes after the detectors is also very important. So you more or less have a chain, an observation chain, and the whole chain has to be good. There's development for the future, which is the spectrograph. And something they mention on these web pages I searched is also there are regular daytime observations. It's quite efficient at an observatory that you can use day and night. Probably by day they use long-wave infrared, I would assume. But also in short-wave infrared you see a little something during the day. And users can decide if they want to use the facility remotely, but there is a local operator there, and you can Skype with this operator and say some things about how to collect the data, this kind of thing, and this gonna help you. And there are target of opportunity programs, and that's something very special because in most observatories you apply for the time, and this has to be fixed 6 months or a year before you collect the data, and then you have no flexibility. You will just get these and these nights. If you have bad weather, bad for you, and the opportunities pass and you haven't detected what you wanted to detect. And here they can swap or change time. You will lose your time at a certain time point and get it back in a different time, this kind of thing, which makes it easier to react to events that just came up. The geography, I don't have to say very much because I used the same picture as last week for the UCURT. I told you that this is the UCURT, the 3.8 meters telescope that has been decommissioned. And here is the observatory we are talking about now, the IRTF. We'll see more pictures of this observatory. But as I told you, they were built in the same year. They have the same range of mirror size. UCURT had 3.8 meters and IRTF 3.2 meters telescope. But this one is still working, whereas UCURT is being broken down. And as we know, on Mauna Kea we're on 4,200 meters. And in the perfect range, northern latitude, to have good weather. It's not, when you count the nights per year, I think it's not as good as the Chilean observatories, but it's still in international comparison very good. I don't have the actual number of how many nights you can use. As you see on this photo, it's the same thing that you have on all large observatories that you have regularly fog or clouds down there and the top of the mountain is clear, which makes the conditions really, really good. And now I'm gonna mention just randomly some results because it was difficult to find results. They haven't put up lists of the papers or anything. So I just grabbed what I could find. Again, also in this observatory, they observed the crash of comet Shoemaker-Levy 9 onto Jupiter, as you can see on the two pictures on the right. And they also, for example, observed the core of comet Hale-Bopp. This is not, of course, not a picture by this observatory. This is just a wide view of comet Hale-Bopp, which was the brightest comet that I saw in my life. I think the core alone was -2nd magnitude or something, so even under a street lamp you could see Hale-Bopp without a problem. It was hard not to see comet Hale-Bopp. It's not accidental that they look at comets and planets, because that's part of the dedication of this telescope. Here I list some wider results from the solar system as examples what this telescope was actually built for. They observed clouds in Titan's atmosphere. They are characterizing near-Earth objects, especially their diameters, and here they say often they use MIRSI for that, this detector suite. And they follow up often on Pan-STARRS data, because Pan-STARRS 1 and 2, by the way, are also on Mauna Kea, or in Hawaii at least. They basically detect near-Earth objects, and then they have to be followed up and characterized. And the Pan-STARRS telescopes are a bit smaller and built for survey, so they probably have much shorter focal length than IRTF. So that's a share of work between the two types of telescopes. First Pan-STARRS, then IRTF. These are called Earth defense efforts, although our technology in detecting near-Earth objects has greatly improved, but what we can do is relatively limited so far when it really comes to defense. It's a bit of a unmodest term here. Often the observatory works with satellites and follows up what satellites found. For asteroids, or planetoids as we would call them in the German-speaking regions of the world, the telescope measures albedos and sizes. It's quite a typical application for infrared telescopes, because in visible range telescopes, that's not something you can do. If you see the magnitude, measure the magnitude of an asteroid, you can't tell if it's a very small icy one or a very large dusty one. Whereas in infrared it's much easier to calculate the sizes and then the albedos in the visible range. So this telescope does actually both. It takes visible range and infrared and then compares the two appearances of the same asteroid. I think even measured with the same instrument. For comets, it's very interesting to do near infrared spectroscopy, and they mentioned that for apolar molecules like methane, or this is carbide, I think, they are not visible in radio observations. That's why it's best to measure them in infrared. And this is still an interesting point about comets, how much volatiles they have of the different sorts, and where do they start having a head enriched with these volatiles. We talk a lot about the water, but another thing is the CO2 and the CO. And obviously also more complex, partly even organic molecules that come out of a comet. And they mentioned that if a comet shows an outbreak, they can obtain a near spectrum within days, which is comes in very handy. Why are some comets a lot brighter than they actually should? Which is actually true for the comet 2025 R3 Pawn stars that I just took a picture one of 2 nights ago. It has 6.9 magnitudes, but the estimation is 15th or so. So it's a lot brighter than it actually should, according to the calculations. Here there's a plot about publications that use the IRTF data, but only of the solar system. The solar system part is shown more concretely, whereas the non-solar system part is just this dark blue beams here. And there are also data libraries, so they are measuring for the library that has started in 2008 and gets more and more common. Excuse me. And the light blue are asteroids and the green ones are comets. Of course, the comets, they are measured if they come up, and this is an irregular thing, whereas planets and satellites is more common. That's something that always astonishes me, how many moons are found every day on Jupiter and Saturn, and sometimes even Uranus. So that looks good because publications in total are on the rise. And the publications are the ones that bring back the money, actually. And they mentioned this SPECS tool, and it is an efficient data reduction pipeline that increases this productivity as measured in scientific papers, reviewed scientific papers. That's a very important specification. And they compare it to the Gemini North, which is a much larger telescope, and say we have the same number of papers a year as Gemini North. Why is that? And they say it's because data reduction is very important and they're good at that. Another field is exoplanet observation, and they are time sensitive, so they can be planned relatively. You can hand in a general project, and then the measuring time points will fixed later, and this is good because often you don't know years in advance when your observations should be made. And as we discussed already in earlier presentations, you can characterize planetary atmospheres with medium-sized telescopes like this one. So many of these exoplanets have been discovered by TESS, and then the IRTF characterizes the planets. So normally you have at least two darkening and events of a star or more, and then you can predict when the next one is gonna happen. And only if the planet is in front of the star you can do these atmospheric observations normally. So you compare the spectrum of the star without the planet to the spectrum of the star with the planet, and then look what differs in terms of absorption or even emission, I don't know, in the spectrum. And the other thing is planet formation. And this is of course connected. You observe exoplanets and wonder how planets are being formed, and then there are theoretical models, and then you can check these models or constrain the models. And the picture on the right is actually not from high-redshift. It's from ALMA, which is in the radio part of the spectrum, but the borders between the infrared and radio are not so fixed. Maybe I will discuss ALMA at some point later, because it's a very important observatory. And it has similar constraints as an infrared telescope. It also has to be in very dry environment. I'll certainly mention it when talking about the Tau telescope, because it's on the same mountain as ALMA. And in the planet formation there are hot and cold start models, and people need data to tell which ones are more realistic. So in hot models, accretion happens by gravitational instability, and in cold models it's more core first. And this of course depends on the chemical composition of these disks around the stars. If there are more heavier elements, cores are easier to build than if there are just volatiles, which is hydrogen and helium. So astronomical speaking, non-metals. Then it's harder to form planets, probably, but we don't understand this completely yet. Going further away from the solar system, what the observatory also does is stars and stellar evolution, and it taps many aspects of stellar astrophysics, as effective temperature measurements. Again, it works with the data of satellites and other telescopes, and then makes follow-up observations, mainly spectroscopy. And also icy dust grains can be observed, and lots of work is put into the metallicity of stars and also into hotter stars. As I just mentioned, metallicity is how many elements do you find that are heavier than helium. And this could influence the development of the stars, also where they are on the Hertzsprung-Russell diagram, how long they live, how bright they are, this kind of thing. And the spectra also complement the work of the JWST, because JWST is more sensitive and it's a larger mirror, but it's not as good as in high resolution spectra as this actual IRTF. On the right I just added a very short and very insightful summary about stellar evolution from Britannica that I can recommend, because these are the kinds of things I have been thinking about for years and never quite understood why some stars are red all of their lives, whereas others tend to be blue on the main sequence. But it has to do with the mass, and here it just shows large mass stars have this blue phase, whereas low mass stars are red all of their lives, especially the ones even lighter than the sun is. And still most of them will become red giants, but not red supergiants. And in the end they form planetary nebulae, but don't have a supernova. And then planetary nebulae can't be observed for very long. And then you just see the white dwarf for a long time. Which is the way for most stars, whereas the mass-rich ones do have one of these two ends, either neutron stars or black holes. But the nebula they make look very different from a planetary nebula. So the IRTF helps also in that. And something quite simple but quite handy is looking at very far galaxies, because their spectral lines are hugely redshifted, for example 2.4, so they're in a completely different part of the spectrum than nearby galaxies. So that's what you can also use infrared telescopes for. Of course, here it would be good to have a larger telescope, like JWST, for example. Now the summary and outlook. This telescope seems to have a bright future in contrast to the UK IRT. There is a white paper that says it should stay a telescope for classic operations. NASA has an interest in solar system and near-Earth objects, so it's probably continuing to pay an annual contribution to this telescope. So this person that is working around the clock will still be paid, and despite the telescope not being a very large telescope, it's still in use. And there's always data coming from space probes that has to be followed up. Like actually most ground-based observatories, it's specialized in spectroscopy. That's not very special, but it obviously has some of the important tools for spectroscopy. And as I told you, detectors can be almost more important than the telescope itself. And of course, the sky you have, so the weather, the seeing, and the clarity of the atmosphere above you. And as I mentioned, the data reduction pipeline is efficient, which also helps. The other thing is the working together from state and universities, and here the state just pumps in money, which may not be the same in all of the observatories. In some, the observatory will be built with public money, but afterwards the universities have to carry the costs themselves. And in this telescope there's also money from NASA coming in, which of course helps to keep it up there working. And here there are two more views of the observatory. It's also a very characteristic building with this flat building and a cupola on top of it. Whereas the mount is, I think, relatively, as the mounts in this time, 79, used to look. These days probably people would build an azimuthal mount and then just turn the instruments, which is easy these days. Easier than building a very heavy mount. Yeah, and in the future we'll talk about more infrared telescopes, because I by no means finished this series yet. So thanks a lot for the attention for today.